Our goal for today is twofold. One, understand this concept of reduction. And we're going to work our way up to it. The only thing we're going to do other than try and understand the concept is to do one example of a reduction of Turing machines and understand the concept. And next Monday, the entire class is slated to work through some other ones. The next 2 weeks, maybe next 3 weeks, is going to be sets of Turing machines. Okay? Technically speaking, every single set I talk about is still a set of strings. We really have a one-to-one correspondence, though, between strings in Sigma star and Turing machines. Starting today, I'm going to just take that as totally implicit so we don't have double subscripts all over the place. I am exclusively going to write my sets of Turing machines this way. Do know in the back of your mind that this reg bar is really a set of strings. The strings are the indexes of those Turing machines. Okay, so we're still talking about sets of strings, but when we use these sets, we're going to freely interchange between the index of a Turing machine and the machine itself, and we know a UTM can do this. So we're going to blur that just a little bit. That's why I spent some time being very explicit about it last class. Okay? Our key consideration is, okay, are these sets like this, there's going to be more. How hard is it to answer the question? Here's a machine. Is the language that accepts regular or not? Here's a machine. Is the language that accepts finite or not? Here's a machine, does it accept the empty string? Here's a machine, does it accept every string or not? Here's a machine, does it accept any strings at all? These are the sorts of questions about Turing machines we're phrasing, okay? And remember, for a machine to accept one of these sets, it's going to take a single machine as input and have to answer correctly, yes if it is, or no or loop if it isn't, whether it has that property or not. Our inputs are now kind of machines, and we're going to do something with that machine to see if it has certain properties. Okay? We did talk through this, and this I won't go through the whole thing again. We talked through how you might at least, this is part of the game for all of today once we get to the example, how you might check whether a given machine is in null or NULL-bar. You know, you might take a UTM and run that machine, a machine you're given. You might run it on all of Sigma star, more and more strings, and see if it eventually accepts one. If it does, then your machine is definitely in NULL-bar. And if you never find a string that it accepts, it's actually definitely in null, but you'll never know because the looping, right? You'll never know for sure that a machine is in null, okay, via a Turing machine. So we saw, for instance, that NULL-bar was RE. Null was not RE. So we haven't proven that yet. Null was co-RE. Doesn't seem to be recursive. We'll be able to prove that by today. I think that's our first example of a reduction. All this on handout, so I really want you to think and ask questions. I mean, I want to take this as seriously as you can this whole semester. We don't have a whole ton to do today, but what we do have to do is sometimes a bit subtler or deep. I want to do, I'd say, a simple reduction example. If you saw what the file is called, I would actually call this a toy reduction example. This is removing some of the technical difficulty out of reduction to get the idea down, okay? Here's the point. A question, a silly question that you all could answer. In fact, a finite automaton could answer this question. Would be, is the number expressed by some string, make it binary or make it decimal, I don't care, divisible by 100 or not? Okay? How would you check if a decimal string was divisible by 100? Ends in 2 zeros. If it ends in 2 zeros, it's divisible by 100. If it doesn't, it's not. You all learned that in grade school, right? I am intentionally choosing a super easy problem. In real life, these will be extremely difficult problems. So pretend that you just know that your question is to see whether a given string represents a number divisible by 100 or not. That gives you the problem defines a set of strings. The set of strings y such that the number is divisible by 100. That's the problem versus string thing we saw before. Okay? This is not a very complicated set of strings. Suppose that you have a Turing machine overkill. You could probably write a Python program UTM kind of thing, Python program to check if a number is divisible by 100 or not, a string, right? Easy? Okay. Now, just for suspense of reality a little bit, pretend that this was a more complicated set, right? A more complicated problem, but you had a machine accepting it. Okay, so squint your eyes a little bit about whether it's divisible by 100 or not, because that's a really easy problem. I want to phrase a second question, and what we're trying to do with reduction, this is what we're leading into, is relate the complexity of two different sets. We're going to try and say this set of strings is at least as complicated as this set of strings. Okay? And reduction is how we express this comparison and how we eventually will be able to prove that one set of strings is is at least as complicated as another set of strings. Or said another way, this set of strings is no more complicated than this set of strings. We're going to have kind of a hierarchy of difficulty of sets of strings. So here's my second question. There's always going to be two questions. There are going to be two sets when you're doing reduction. That's complication number one. Question in green is whether the number is divisible by 100. Related question in blue is whether the number is divisible by 10. You all know how to check that as well. How would you check the number is divisible by 10? Ends in 1, 0. That's the relationship between these two sets. We could form a set A of the strings where the number is divisible by 10. These are the strings that end in a 0. These are the strings that end in 2 zeros. These sets are not unrelated. What I'd like to say is this. Pretend for a second that the green problem's a lot harder and that the blue problem's a lot harder, because it will be. So don't do something cheating-wise. But I want to ask you a question. And I want no one to yell it out, because I want you to think carefully. I want everyone to think about this carefully. This is one of the easier questions for today. If I told you I could hand you a machine that would check if a number was divisible by 100 and in 2 zeros, and that machine you have in your hand, and you can use it to answer questions. And I said, if you have that machine in your hand, does that make it somehow, is there an easy way to check if a number is divisible by 10? How could you use a machine that tests divisible by 100, all the machinery in that, to really simply check if a string is divisible by 10? Now just pause. The number given by a string is divisible by 10. Think about that for a second. Everyone got some thoughts in their head? If you want to say it this way, the green machine is going to check if a number ends in 2 zeros. This is going to check if a string ends in at least 1 0. There's a way the green machine can help you answer the blue question. I'm sorry, they're super easy questions. That's why this is the toy example. I want you to see the general principles first. Okay.
Can you modify the strings going into the machine?
Right? How could you take a string you're asking if it's in the blue set and modify it to let n answer the question for you?
Multiply it.
Multiply by 10 or add a 0 as a string. Either way, yeah. So here's the point. The question of whether a given string gives you a number divisible by 10, I should probably say number of x, but whatever, is equivalent to the question if and only if the number with an extra 0 is divisible by 100. So here's the point. Don't worry about the fact that the green machine's really easy. You can code it in Python in about one line. And the blue machine is really easy too. See the relationship without the complication yet. The machine accepting the green set allows you to answer whether a given string is in the blue set really easily. You're using the green machine to answer the blue question. How you do it is by changing the thing you're asking the question about. The question of whether x is divisible by 10 is equivalent to the question of whether x with an extra 0 is divisible by 100. You're going to change the thing you're asking the question about in such a way that to answer the blue question, you change your object you're asking about and ask the green question instead. If there's any questions at all about this, all we're going to do is take this idea, be a bit more explicit about it, and put it in a much harder context. But the idea is using a machine you have to construct an easier machine, a machine to answer maybe an easier question by modifying the thing you're asking it about. Okay? This process of changing the string x that blue's asking about into a string to ask a corresponding question about green is a function. The question I'm asked about in blue, I'm going to add a 0. X maps to x0. That's add a 0 is the function here. is the thing you'll do to change the string you're asked about in the blue question into one that the green machine will answer for you. So we're talking about transforming the thing you're asking about. Yes, great.
Does the direction like matter? Like,
yes. Oh, 100%, yeah. I'll let you think a little bit about this. You'll see this come up very explicitly later. There is very much a direction, and I'll say this right now. I'll put it in red at the bottom later in the slides. I'm going to say it right now. This function is going to be what's called a reduction. A reduction is simply a function that changes one object you're asking a question about into a different object to ask a different question about. I'll talk about the details in a second. It may not be clear which question is actually harder if you can do this, but it will be clear in a second. But there is a direction. Direction definitely matters. We'll eventually write this relationship with a less than or equal to sign. And it may not be obvious what the quote-unquote harder question is until we get to some details. But the key property, a reduction is a function, again, that changes the string you'd ask a question about in blue to the corresponding string to ask a question about in green. And the property it's supposed to have is that a string is in the blue set if and only if its modified version is in the green set. Now, there's several moving parts, right? There's two sets, the blue set and the green set, okay? There's a function that maps strings that you might want to check. You know, from strings being checked in the blue set, that's the x. It may or may not be an a. Sigma is supposed to be a function that changes that to a string for the green set, and the same thing happens. A reduction from one set to another is a function that modifies the strings you're asking about, such that the input string being in the blue set is equivalent to the output string being in the green set. This is the picture to understand. I'll give you a copy of everything from these slides on a piece of paper. It might help you to write this stuff down, but more important is to ask questions. This is the picture. All strings are the circles. By the way, alphabets don't even have to be the same technically. The set A, the problem or set you're trying to analyze, breaks that set of all strings into two pieces, the ones that are in A and the ones that aren't. The set B on the other side breaks the set of all strings from that alphabet into the strings that are in B or aren't. What you're trying to do is have a function that maps the yeses to the yeses and the nos to the nos. It respects that dotted line. A string that started in A bar ends up in B bar. A string that started in A ends up in B. And there's very much as a function of direction here. Question? A little bit outside. Okay.
So the reason that they can be in different alphabets is because of the reduction that can change everything.
It could take zeros and ones to x's and y's. It didn't make any difference. Now, most of the time, the alphabets are zeros and ones for us. Might be some other symbols. Usually it's zeros and ones, but it could be really anything, right? Question?
Does this have to be, or like clearly it's not one-to-one?
Doesn't, yeah, it's a very good question. Those of you who've seen anything about functions before, that's a very good question, especially if you've seen some math, anyone who's seen some math. This is nothing like a property you've seen in math. All you care about is that it maps things in A to things in B, and things not in A to things not in B. It's the simplest, it's simpler than any condition you see in a math class. It doesn't need to be one-to-one, doesn't need to be onto. The only property, and it's a very simple property to have, the function moves things from this context to this context, the blue context, the green context. And when it moves things, it moves, again, it respects the division into in and out. The stuff in A maps the stuff in B, the stuff not in A maps the stuff not in B. This literally is what we're trying to study for the rest of class today and all of class on Monday. Yeah.
Does this function have to be like invertible? Like can
Nope. Absolutely not. The more you know about functions, the more I want to make it clear. None of the properties you're used to caring about matter here. It just has to be a transformation. It has to take every string in A and has to map it to a string in B, but it doesn't have to be onto, it doesn't have to be one-to-one, it doesn't have to be anything, it doesn't have to be invertible. It's got to take every string not in A and map it to a string not in B. But that is literally all we care about. Nothing about invertible, injective, surjective, one-to-one, onto, whatever you want to say. Nothing else matters.
I think the answer is yes, but can this function switch sigmas? Like,
Yeah, oh yeah. So there could be different alphabets even. Yeah, 100%. For our context, it won't very often, but it could. For instance, you might take a question about whether a string has the form a to the n, b to the n, c to the n, and change it into a question about a string having the form 0 to the n, 1 to the n, 2 to the n. Those are pretty much the same question. That's a reduction that would be really easy to write. But it should be transforming the objects you're asking about, which could change alphabets, in such a way that the question translates. What you're going to have to do when you do a reduction, by the way, there's two parts, but the second part's two-part. You have to find the function and justify that has these two properties. Sorry about the sigmas. The function for the rest of class is going to be a sigma, okay? And inherent issues, there will always be two sets of strings you're talking about for reduction. You're trying to compare complexity of the set A and the set B. Now, it may still not be clear whether this makes A or B the more complicated set. We'll get to that. But step one is, if this is literally it, this is what a reduction is. Those three lines, this, and this one's just these two. That small amount of information is all you need to know about what a reduction is. Now, the context we're applying it to is way more complicated. It's actually going to be a set of machines transforming into a different set of machines. Machines maybe being in some set or not, turning into machines being in some other set or not, like null or NULL-bar or HP or whatever. The objects are more complicated, but the entire context of what you're talking about, this is all a reduction is, capital I. Before I put this slide down, I want to make sure that the idea is there. In our case, right, it was strings, if they were both strings of zeros and ones, maybe, or maybe 0 through 9s. X being divisible, being a number divisible by 10. If and only if x with an extra 0, that's what sigma did, add a 0, it's a function, is divisible by 100. It relates these two questions. Okay, relating the questions is going to be harder than adding a 0 most of the time. The sets will be sets of Turing machines, but this is the diagram you should think about. Trying to find the sigma that does this. Okay, a sigma that does this. That's the reduction is the sigma that has this property or these two properties, either way you want to say it. We're going to be changing the question by changing the object we're asking it about. That's what reduction does. Okay, here is these symbols. Oh, I've given it away now. Problem with this terminology, I gotta say, I don't like it. There's a lot of things I don't like with the terminology. It's classical terminology, whatever. If you can get a reduction from A to B, and again, there's a direction of this function, right? Here to here. Blue to green in this case. That means that the thing you're mapping into is actually at least as complicated. That's how you should read this less than or equal to. Less than or equal to is for numbers or whatever. Less than or equal to M is like for machine. Somehow machine more complicated than A. Now, this allows the fact that A and B might be the same complexity, might be equally complicated sets. But it allows for the fact that B may be more complicated and A would have to then be less complicated. Okay? Why do we care? Right? What a reduction buys us is why it's important. What it achieves is this. My original question was, if I had a machine accepting B, do you end in 2 zeros, or divisible by 100, I can use that and a reduction to build a machine accepting A. The B machine will answer the A question if you're careful. That's what reduction gives you. That's why the B set's more complicated. Being able to solve B plus a reduction means you can solve A. How would a machine be phrased? Now remember, machines take inputs and they accept or reject, maybe loop. Given this machine that checks if a string ends in 2 zeros, how does the reduction, I've erased it, how does the reduction allow me to make a new machine to answer this question? Well, I'm given a string X. I want to see if it's divisible by 10. All I do is make a new string, applying sigma to it. In this case, it was add a 0. And I run n on it. Okay? Because the answer n gives for sigma of x, whether y is in B, is equivalent to the question of whether x is in A. So the answer this gives will be the right answer. That's the point. This is the short idea for how a reduction works. Given a string, you want to see if it's in the blue set or not. You move it via a reduction to the green set, and the question keeps the same answer. In A, in B. Not in A, not in B. The question's the same if you modify the string. The answer's the same if you modify the string. A reduction from the blue to the green, and a machine that will accept the green set gives you a machine that will accept the blue set. I think the diagram's a little bit helpful. There are things moving around. You want to know whether a string x is in A or not? Change it to a string sigma of x by adding a 0 and let n answer the question for you. I can reduce the question of divisible by 10 into the question of divisible by 100. Now, if the question of being divisible by 100 is hard enough that answering it lets me answer this question, then it seems like the green set's a maybe more complicated set. That's the point. Next landing spot. What a reduction is, we saw. Now we're seeing what it gives us. It's their transportation from blue world to green world that lets you change a question in blue world to a question in green world. Okay? The machine that answers the question in green can be used to construct a machine that answers the question in blue. Yes?
Can you have multiple machines with a chain? So it's you have, instead of just having 2, you have 3 instead, 3 machines that you're trying to use a reduction on?
You will do it one pair of sets at a time. So you could do lots of different reductions. The point of a reduction is it reduces one set to another set, one problem to another problem. Okay? This is the entire toy example on one page. So I want to take a pause here and see if there's any questions that hold about this. We had, again, the green problem, the green set, and the machine that answered the green problem, or accepted the green set. Okay, if the green thing's answered, this is why it's kind of harder, the reduction allows me to answer the blue question as well. The point about the reduction is, changing from blue to green via sigma does not change the answer to my question. Yeses mean yeses, nos mean nos. So it's valid to move the string over and have n answer it instead, and that's exactly what the machine does. This part you will never have to do again. It's the same thing every time. Esdras.
I guess it's a silly question, but it works for every input of A. I mean, it has to work for every
string. And in fact, what you're going to have to show in your problems, you'll have to do 3 things to show that you've got a reduction. 1, tell me what the function is. Construct this machine in some sense. 2, double check that things in the blue set are in the green set after you map them, and things not in are not in. There's going to be 2 little proofs inside every reduction. You're going to have to construct the function. And for all the reduction in this first 2 days of it, I'm going to give you the reduction. I want to make sure we understand how to analyze it. There are certain tricks of the trade. Finding a reduction can actually be difficult. And it's going to seem daunting at the very beginning, but you get informed by examples you've seen. Okay? Sorry about the symbols. There's a little diagram. A lot of symbols flying around. The notion is that A is no more complicated than B. And again, the wording reduction makes it sound like the direction of the function makes things smaller. It doesn't. It shows the A set is no more complicated than the B set. The B set's actually the more complicated one. So reduction does not reduce complexity. It shows potential increase in complexity. But that makes sense. If being able to answer green automatically lets you answer blue, then green can't have been an easier question. You can't answer a hard question by answering an easier question. Yes. Oh my God, sorry. Way outside and high. Okay.
When we talked about complexity, is there also a size component of okay, this blue set is maybe larger than the green set in most cases?
Turns out, well, first of all, in general, size of a set has almost no impact on how complicated it is. Except that finite sets are really simple. All of our non-regular sets even are infinite, right? So we're always talking about infinite sets. They're always countably infinite, if you know what that means. Size of set won't matter. The one sense in which you might be getting onto something is the function need not be one-to-one. It could map a whole bunch of input strings to the same output string. As long as the answers match up, that's all you care about. The blue answer for the original string has to match exactly the green answer for the output string. but there could be lots of collapse happening. You could, in principle, have a sigma that maps all the strings in A to one string in B, and all the strings in A bar to one string in B bar. That would still be a reduction. It's just a general fact that a function can kind of have collapse and make the set smaller, but the size is never the consideration. Yeah, just a side effect here. So yeah, this is not about size, it's about complexity. Ideally, we'd have 2 classes, and I'd say percolate on that over the weekend. We don't have time to, we've got only used probably half the class by now, maybe less. So, you might be able to guess where we're going with this. You've seen a toy example of reduction with some very easy problems and just divisibility in strings. You've seen the sets we care about are actually sets of Turing machines. What makes this topic difficult is we're going to do this, but for sets of Turing machines. So, to move it up to the context we actually care about, and this is the big picture of every single thing you're going to do for the rest of today and next Monday, and in reduction problems on the exam. Our sets of Turing machines will in general be the sets we're talking about. First of all, it's 2 sets of strings to begin with. Our actual concern is 2 sets of Turing machines. So the objects are a level more difficult than just adding 2 zeros to adding a 0 to the end of a string. Okay? The blue objects, the x's, will be machines. Or maybe a machine and a string, as we saw in the case of the halting problem. But almost always it's one or the other. There's always a machine involved for us. And there's in general also sometimes an input string. Oh, question, yeah.
Can we map a Turing machine to a total Turing machine?
It depends on the reduction. We might. It totally depends on what the blue and what the green set are that we're concerned with. There's always 2 sets of Turing machines in question. Doing a reduction will take a machine in or not in the first set of Turing machines and map it to a machine in or not in the other set of Turing machines. A machine with some property turns into a different machine with a different property, and the same operation takes a machine without the property and maps to a machine without this property. So again, our source for our function sigma will be a machine or maybe a machine and an input string that either has some property or not. This is in HP or not, for instance. Okay? And we're going to map it to a new machine. And again, this is the equivalent of adding 0 in the string case. Our new objects are machines. What can you do with the machine? You're going to make a new machine out of it that will somehow, in some central cog way, use the machine you were given as part of its running. It's like the engine of your new machine is the machine you were given somehow. So you expect to see in this is your sigma, you're going to take these 2 ingredients and use a UTM to do something with M and Y to answer a different question. That's what the sigma is. So instead of taking a string and modifying it to make a new string, technically we are doing that. We're going to take a Turing machine and build it into some bigger Turing machine to make a new Turing machine out of it. Okay? You might make an analog to you have a motor and you want to make a linear actuator. You want to make something that pushes something in and out, and the motor just spins. You're going to take the abilities that you know this does or doesn't have by being in or not in the set and turn it into a new machine that now has some other behavior. You're going to try and change behavior. I would almost call this adaptation or modification instead of reduction. Reduction sounds like it's making it smaller. It's not. You're going to take a machine in general in and make a new machine out of it. Our first example, our only goal today is to, any questions that come up, ask them, and go through in completion 1 example. We're going to do a reduction that's going to reduce HP. Now that was one of our key things we worked hard for. It's a NULL-bar. We're going to get a reduction of HP to NULL-bar. Now, if you remember what reduction is, it's going to have to take an input, which is a string that is either in or not in HP. I use the bar instead of not in. It's either in HP or not. And it's going to build a new machine that either is or not in NULL-bar. What does it mean for m hash y to be in HP? What's the definition of HP? For a given string m hash y to be in HP means that that machine halts when you put y into it. Yeah, so maybe it's simpler than you may think it is. RE, don't worry about RE yet. The reduction has nothing to do a priori with RE, co-RE, or recursive. The conclusions of reduction will have consequences on these. But what I'm going to need is, if my M halted on Y, I'm going to want my new machine to be in NULL-bar. And what does it take to be in NULL-bar? To accept at least one string. So I want situations where M halts on Y, this construction, this green box, I'm going to use the M and the Y somehow to make a machine that accepts at least one string. I'm going to want, if my machine doesn't halt on Y, the same construction should give me a machine that accepts nothing. Now, some of you may already see how to do this for this example, but we're going to work it through really, really carefully. This is our example that we want to do. We want to do a reduction from HP to NULL-bar. Notice that which one the bars are on matters. It's HP to NULL-bar. So M hash Y being HP means that our new machine's in NULL-bar. And M hash Y and HP bar means our new machine's in null. We need both things to happen with the same construction. So the construction is very, very careful. It needs to satisfy two properties to work. Again, this may help once we finally get to the example. You'll see at least an explicit example of it. This is what a reduction would look like. In fact, every reduction you do in this course will kind of have this shape. A machine, or maybe a machine and a string, use those to build a new machine. And what you need is, whether your input had a certain property or not, makes your new machine you constructed have a different property or not. Good, questions? Yeah.
So here, is the function here, is it just modifying the Turing machine, like in terms of accept state or reject state? For example, here we would probably make like all accept and reject states an accept state so that it shows up in NULL-bar.
We actually, in practice, we won't actually, because this could be any machine M, we don't know much about it. Most of the time, with one exception, our reductions will simply take the machine they're given and somehow run it in a UTM in a particular way to get this green machine to do something. Or maybe take the machine in a string. By the way, every time you see a machine in a string as your input for a reduction, somewhere in your new machine, you're going to run M on that string, maybe with time sharing, maybe one step at a time, whatever. You're going to use this machine on this string. But in general, you're going to be taking a machine or a machine and a string in and making a new machine out of it.
Yeah, what does this modification process look like? Is it a modification of states or?
It's going to be pseudocode. Good news, right? No, we're generally not going to be talking about states or transitions or anything. We're given a machine, and our new machine will be written in a UTM. It'll be telling me what to do with M and or Y to make a new machine out of it. Yes, Esdras.
Is NULL-bar a UTM or?
NULL-bar is a set of strings.
But then we're talking about a machine being accepted by another machine. So it's just a Turing machine accepting another Turing machine. I thought only UTMs do it. Yeah. So I'm trying to conceptualize that. Yeah, I don't.
So the concept is this. The objects are machines, okay? The machines that come in will be in or not in some set. You're going to build a new machine out of that, maybe using it as a little engine inside of it, put some other machinery around it to make a new machine. You're going to describe it as, because you're given a machine, to run that at all, you're going to need a universal Turing machine. So what you're going to do is give some pseudocode instructions on what to do with the machine you're given to form a new machine. The new machine is the full set of instructions of whatever you put in this box, what to do with M and Y. And what you need is that new machine you've made to either accept at least one string or not. So the reduction thing for the just add a zero and talk about divisibility is still what reduction's about, but now the objects are Turing machines. So your input is a Turing machine maybe that has some property or not. Your output is a new Turing machine using that Turing machine somewhere, saying how to run it, and this new Turing machine has some other property or not. So this is divisible by 10 or not. This is divisible by 100 or not. And this is add a zero. This is just a lot more complicated because it's Turing machines.
I know you said not to worry about sigma too much.
I mean, it's a function. It's computable.
Does
It's a
it
computable function.
have to be? It's computable, and does it have to be like equal to or less than the complexity of the functions involved? Because I could imagine a situation where you could like cheat with sigma by like solving the problem in sigma, and then like if you were trying to use this to talk about like recursive, but all sigma has to be is computable, then I could see a sigma that is doing something that a TTM can't do.
Well, so to be clear, sigma is going to be a computable function. The sigma is the writing of the code. If you gave me the m and the y, I could write this code in a UTM, and that would be a computable thing to do. The process of doing sigma is going to be 3, 4, maybe 5 lines of code. And the computability of sigma is that you could take the m and the y and literally write the words around it to make a new machine. You'll see an example. You will see exactly that this is the example. So before we get into it, trying to get some general sense of what we're trying to do is important. But this may be helpful once you see actually what the construction looks like. This is the big picture of what we're about to do. Estrus, nope.
After modifying m,
We'll get a new machine.
yes, will the machine be the same across all inputs?
Yes, that's the key thing. The words you put around the m and the y in this case have to be identical because it needs to work on m hash y, whether it's in HP or HP bar. And the new machine, via the same construction, very important, has to either be a null bar or null accordingly. So finding this way of building stuff around the m and the y is the hard work, right? And again, how on earth you would do this is going to take a long time. We're going to work through an example today and several examples on Monday to help flesh this out. And it turns out the examples you've seen in the stuff we do today and Monday will be informative on how reductions will work in general, say on the exam, right? I'm not going to ask you to invent a new kind of reduction that you've never seen before on the exam. The same way for the pumping lemma, I'm not going to give you a set unlike anything you've ever seen before, right? So study carefully the examples you've seen and see how they work. So again, we will start with some kind of machine or maybe a machine of string. We will be producing a machine or a machine of string, and we will be concerned with what strings it accepts in general. Okay. How would you check if a machine was in null bar for it? How will you justify the strings that this new machine's in null bar? You have to show that it accepts at least one string. How will you show that in this case the machine needs to be a null? You'll have to justify it doesn't accept any strings.
I'm thinking about something, but I don't know if it's correct. You said to find the reduction, you input the machine into a UTM, and then
It does something with it.
okay, and then you find, because previously we've seen that the UTM can return the index of a machine that accept. So basically, you through the UTM you find the machine like that accept the string, that answer the question for the string, and that's the machine. Is that that the pipeline? Okay.
Yeah. So I mean, technically speaking, and this is the part we're suppressing because we got enough to deal with already. The things you're given are not actually machines; they're indexes of machines. And the thing you will produce is technically a string indexing that machine. But if you can tell me what the code is for the machine, I can turn that into an encoding and find its index. So I'm not worrying about that part of the translation. That's a technicality we're not going to get into.
In the like simple example,
Yes.
we were given the green machine, which we used, and we didn't have the blue machine. Is it flipped here in that we have the blue machine and we're creating the green machine?
Good question. So we will see how the conclusions run, and they always can run the same way. So that justifying that a reduction means that this set's no more complicated than that set is going to be boilerplate every time. But what was your original question? I forgot.
Like in the simple example, we were given the green machine.
Yeah, that'll be boilerplate. We'll see it once and for all, and it'll work for all reductions. That's not something to think about yet. Okay, that's the easy part of reductions. This is the hard part. The details are the hard part. This machine was actually our string of zeros and ones, or 0 through 9. And Sigma was modifying it to a new string. It's just that now it's a machine and changing to a machine. We haven't seen that next level yet. So what this tells us, I think we're going to see very shortly.
The green machine here will be a like running in a UTM.
Yeah, UTM is a Turing machine. That's okay. Yeah.
But does that not mean that it's becoming more complex that it's running in a UTM?
I don't know if I would say that.
Because it's going to be a Turing machine inside of a Turing machine.
hold that question for now. Don't worry about that part yet. Step one is to understand what a reduction is and see a reduction. Then we will see what it tells us. And that's where the fact that there's a whole second level of machines coming afterwards, don't worry about that yet. We're trying to compartmentalize this. So first thing is to understand how to kind of do the take an input, which is now a machine, do the thing in adding a 0 to get a new machine. Don't worry about where we go after that until we figure out the reduction part first. But the conclusions are going to be really easy. That's not the hard part. Yes.
Yeah, I have a question. Depending on the answer, I have another question. And my question is: so is the UTM the ultimate source of truth, that we use to find
the UTM? To take a machine and build a new machine out of it, you're probably going to try and run it somehow. These will always be pseudocodes for UTMs or for UTMs. Things that can run the machine. You're given a machine. Sigma is a function that takes a machine and outputs a machine. The machine it's given will somehow be integrated into a new machine, and the way we put a little machine we're given into a new machine is via UTM. So our Sigma will always be, take whatever you're given, add some words around it in pseudocode for UTM, and that's your new machine. Whatever M did, let it do its business somewhere inside your machine to make something happen. Again, this is way too abstract to see the details. Once we see an example, you'll probably have a better feel for this, but yeah.
But M prime exists inside UTM.
M prime is a Turing machine. It is implemented via universal Turing machine, 100%.
Oh, so the UTM doesn't.
M prime's the machine. M prime's actually a machine.
Oh, I guess.
It's a machine that will probably run the machine you were given in some way or another.
So the UTM doesn't run like an infinite number of machines across like.
Oh yeah, this is all one at a time. A input string, just like adding 1 0 was one string at a time. Give me a string 190, add a 0, 1900. Give me a different decimal number, add a 0 to it. The same rule works one input at a time for any input you're given. Given one machine, you'll do the same thing to it and make an M prime out of it. Given a different thing in blue, you'll build the stuff around it the same way every time and get a different machine, but only has to work one input at a time. This sigma is a function. It's going to take things that are either in A or not in A, one at a time, and map them to a thing in or not in B.
So I guess my question is, how does sigma do that?
Literally, it's going to take a machine or maybe a machine and a string, and it's going to write words around them into pseudocode that tells what a UTM should do, and that UTM is the output. The M prime is code for a UTM to run that somehow integrates the machine you're given into it.
I was just going to ask, can you apply closure properties to machines? Because it kind of almost feels like the reduction kind of almost like for M prime kind of feels like a union. No way, or maybe I'm just interpreting.
Yeah, it's an integration. I mean, you're going to build other code around that machine. It's not exactly a union, but you're adding more stuff around it. Again, my best example would be if you have a piston, right, that's supposed to move in or out, and you have an engine which always spins around, and you want to turn it into linear motion, you're going to put other machinery around to make it do something else. The green is the other machinery around the little engine in the middle. Other questions for coming? Oh, Toby, I guess.
So HP is machines matched up with the string that they halt on. Null is just machines. So is M prime just like ignore its input basically? It's not based on.
You've been given an M and a Y, and whether that's an HP or HP bar depends very much on what the Y is. So if you're given M hash Y, you're probably in your machine going to use the M and the Y. But this new machine only takes a string as an input.
I understand sigma
Yeah.
based on M hash Y, but like M prime
is a new plain old Turing machine. It takes one input string. That's all. Yep.
But because the set is defined as like terminates on, or is null for at least one input or not, like M prime doesn't actually use its input. It just uses.
Oh boy, oh boy, oh boy. That is this particular reduction, you're right. More complicated ones it will. But you're right. M prime will actually ignore its input in this machine. But that's a very easy, I hate to say it. This is a really easy reduction. Sorry, it's going to get worse on Monday. We have to work in steps. The first thing is to understand one reduction. This is the reduction we want to understand today. All I'm going to give you for what I want you to do before Monday is review what we said today. Big picture, what's reduction about? How did the toy work? How does that let us answer questions in one context or another? How did this one reduction you've seen work? Pour over it. You've got Thursday, Friday, Saturday, Sunday, and most of Monday, plus the rest of tonight. But I'm not saying you should spend your entire life on this problem. You have one example and a context to look at, and you're going to see more, like 5 more examples on Monday. That's the goal, to get a real sense for what this is doing. If you understand it today, great, but what you're going to see is a very limited example here, because this is complicated enough already. By the way, I would say this, getting an understanding of reduction, if it motivates you, will put you in extremely rare error in the universe or in the world. Like, people consider calculus to be a really difficult subject, but honestly, lots of freshmen all over the country take calculus. This is one of the more substantive things in a 300 level CS class. Okay, so you're trying to earn your way into something really substantial by understanding this. And it will be hard. Obviously, if the hardest thing in CS 301 isn't a little bit hard, then what are we doing, right? Okay, that's the end of this slide. This is all the prep I can give you for one example of reduction, which is the rest of today, and then we'll chase it home. I'll give you one more piece of paper. You don't have the example yet. What I would say is, if you look at your handout you already have, it's what we've said so far. You had your toy example, you have the picture of how this kind of is supposed to work, you have some more discussion of how this is going to work in the context of machines. We're going to do this reduction next. All that's left for the class is do the reduction, make some conclusions, and hopefully tie things up a little bit. Here is our big picture. Now, I'm going to make some of these more explicit now. Sigma will be a function from sigma star to psi star. Don't worry about psi. You can have 2 different alphabets if you like. It's going to take strings in one alphabet, every single one of them, and map them to strings in possibly another alphabet, but the alphabets aren't our concern here. The alphabet could change. The key thing is that a string in or not in A will map correspondingly to a string sigma of X in or not in B. This is still your picture. Sigma star is your input alphabet. Psi star is your green output alphabet. You're going to turn an object, maybe a machine in a string, I don't know, whatever, that either has or doesn't have some property. And sigma is going to, via the same rule every time, map all the things that have the property, the things that have the other property, the green property, and all the things that don't have the blue property and things that don't have the green property. That's all a reduction is. In our example, this will be HP, this will be NULL-bar. Here is our construction. This is one of the shortest reductions you'll see is 3 lines. The longest reduction you'll see will be maybe, it depends if you talk about next Wednesday or next Monday, 3 or 4 or 5, maybe 7 or 8 at the most. These aren't overly complicated things. But what I want you to see is that from blue to green is a computable operation. If you're given a machine and a string, you can simply add the green code around it, and you have a Turing machine. This is what the output machine is supposed to do. Given m hash y, I'm going to make a new Turing machine. Input m hash y, output this, and if you remember the empty box with some dots and m and a y, all the green stuff is what I'm filling around it. These are the adapters to make m and y do the right job in the green machine. It's very simple. It's 2 lines. You've seen this idea before, actually. Given an input string, because the green thing is a Turing machine, it's going to take an input string. Okay? It's going to run m on its input y. Whatever m and y I'm giving gives me a new machine. But the transformation from the m and the y to the thing in the green box is the sigma. Sigmas write these words around the m and the y. That new machine runs m on the input string y, as Toby noted, ignores the input it was given, and accepts. Yeah. Oh my God. Oh, almost hit someone with that. Okay, good, yes.
And that means that it's identical, because if it doesn't accept or reject y, it will never get to the accept, right?
Jumping ahead. So I want to make sure everyone's following this step by step. Yaya's running to the next step. Yep. To know this is a reduction, just 2 things to check. the input could be either in or not in HP. I want to make sure the output, what the output set is in, null or null bar. So I want to just ask you, in the case of the input, this is the X, so to speak, M hash Y. If M hash Y is in HP, make sure you know your definitions. What does that mean about M and Y? M halts on Y. Read what that machine will do. For any input string, it will run M on the input string Y, which will eventually finish because M hash Y is in HP, and it will accept. Okay? Think about, that's what M prime does. In this case, in the case that the input's in HP, that machine will accept everything. What's the language of my new machine M prime? Sigma star. It's going to ignore its input string. If M hash Y is in HP, it's a new machine. That machine will accept every single string. L of M is sigma star. Okay? Consequently, what set is my new green machine in? If its language is sigma star, is M prime. The language of M prime sigma star is M prime in null or null bar? Null bar. That's half of what it takes to have a reduction. The reduction is the process of taking M and Y and building a new machine out of them with them used somehow as ingredients in the new project. Okay? And if the original string was in HP, the first line will terminate and you will accept no matter what. L of the new machine will be sigma star, and therefore M prime accepts not more than nothing, accepts at least one string. In fact, it accepts all the strings. So part one is to do the actual reduction function, which is, again, writing some pseudocode using the input. Crucial fact. Your pseudocode works for any M and Y you're given. It's the same operation every time. The words you added around the blue M and the Y are identical no matter what M and Y were. But it has the right behavior every time. What's the other half? Well, suppose that M hash Y wasn't in HP. There's only two cases, right? If your original string M hash Y is in HP, something's supposed to happen. If your original string is not in HP, something else is supposed to happen, but it's the same construction every time. We cross our fingers and see if this is a good reduction. Think through that machine in this case. M hash Y is not in HP. By definition, what does that mean? It doesn't halt, it loops. Analyze how that machine will run. It will take an X and ignore it, throws it away. Run M on Y, and if M hash Y is not in HP, that second step's going to loop. Will it accept? No, it'll never get to the second line. Okay? So our conclusion is pretty simple. M prime, if M hash Y was not in HP, the new machine I've constructed, same construction in both halves. If M hash Y was in HP, I get something true. I get M prime to be my new machine to be a null bar. If M hash Y was not in HP, that machine will loop at step one. It won't accept anything. L of M prime will be the empty set. And you know where this is headed probably now. What set is M prime an element of? Null. Now, if you're disappointed that this doesn't seem as hard as it was supposed to be, I mean, I don't know if anyone's disappointed in that level. That small bit of analysis, if you can write down the reduction, if you can write down the green code, what to put around the M and the Y to make a new machine out of it, and if you write it down carefully, you can arrange that if your input string M hash Y was, if M halted on Y, will give you a machine that is accepting at least one string. And if M hash Y was an HP bar, then your new machine accepts nothing, then you've got a reduction. This green thing in the box is the reduction. It's how to take an M and a Y and make a new machine out of it. Okay? The yes for HP turns into a yes for null bar. The no for HP turns into a no for null bar, or a yes for null if you like. There will always be two things to show for a reduction. Now here's the point. We get to the payoff here. What we've done isn't trivial, and it's consequential. This is what's called a reduction. This is your first example of an actual honest-to-goodness reduction we might care about. This is a reduction of HP to null bar. It's an operation, that's the sigma. It preserves yes and no. between the two sides. Again, I'll make the same comment. This is really, I can't tell you enough how much I dislike this term. Reduction sounds like it makes something easier or smaller, and there's definitely a direction to the reduction. It's from blue to green. But in a reduction, the green problem is the harder one, and the blue problem is the easier one. Doing this reduction means that your blue set is no more complicated than your green set. Equivalently said, the green set is at least as complex as the blue set. It sets up in the hierarchy that blue and green, it's either this or this in terms of how complicated the sets are. Our operation transforms our input machine and string to an output machine. The inputs in HP or not corresponds where the outputs in NULL-bar are not. That was what we just showed on the previous couple slides. There's always two things to show. Please be careful about. There's always two halves to show for a reduction. I might ask you this before we go further. This same reduction actually works for other sets. So take HP and use the same construction. Notice that I took a machine and a string where the halt happened, and I got an output machine that accepted everything. I took a situation where the machine didn't halt in HP bar and got a machine that accepted nothing. The same sigma might work for other sets of Turing machines. Now, the input's definitely HP or HP bar, but what are other sets that I could have had a reduction for? Why was this true? L of m prime was all of sigma star. And in this case, the reason was because L of m prime was the empty set. Here's my question. If you look at your list of sets from last class, there are other green sets that this is equally well a reduction for. It's HP to several of them. Look at the positive one. If you accept sigma star, what are you definitely in? That's all. The same function reduces HP to all. It reduces HP to NULL-bar. So this was originally HP to NULL-bar. It also will reduce HP to all. It also will reduce, if you're careful, HP to... Is there another set on your list that this will get it into? Empty, actually. Remember, empty means that it accepts the empty string. If your m hash y is an HP, you're going to accept everything, in particular accept the empty string. If it's not an HP, you're going to accept nothing and not accept the empty string. This same construction from HP to a new machine does several reductions at once, and that's kind of nice. It reduces HP to NULL-bar because if you halt, you will accept at least one string, and if you don't halt, you'll accept none. It also reduces HP to all. If you halt, you'll accept every string, and if you don't halt, you won't accept every string. It also reduces HP to empty, because if you halt, you accept the empty string, and if you don't halt, you don't. So this is the beauty of it. The same construction of sigma might give you several reductions at once. Oh boy, questions. Okay, Parker first. Yep.
Empty set count as a finite set?
The empty set is a finite set. Thank you. I'm not trying to make an exhaustive list. HP to be careful.
HP would go to infinite.
Yeah, fin bar or infinite, yeah. If your machine halts, you'll accept every string, which will be an infinite set. If your machine doesn't halt, you'll accept the empty set, which is finite. There are lots of reductions. This gives you lots of reductions, this same construction. This same construction will reduce HP to several sets. It reduces to NULL-bar. It reduces HP to all, reduces HP to empty, reduces HP to fin bar. Okay.
Yeah, I'm just curious about the construction. Like, if M accepts sigma star, why? I'm curious about run M on the input string Y. Like, what does it actually?
Well, M hash Y is the input. So the machine's the green thing. The input is a machine and a string that either does or doesn't halt. If the machine does halt, I'll get a new machine M prime that accepts every single string. If the machine doesn't halt, if it loops, I will get a machine that accepts nothing. Those two situations, accepting everything or nothing, equivalently could be in NULL-bar or null. It could be in all, every string, or not all bar, not everything. could be accept the empty string or not. It could be an infinite set or a sigma star or a finite set, empty set. Yeah, it works for all 4 of these at once.
Just the pseudocode, like when you. Yeah. I was asking about the pseudocode because
It never uses the X. That's why it's either all or nothing. It never uses the X. It can't distinguish between the X it was given. It only runs on Y, which is given to it.
Yeah, I was gonna ask about the X, but in this situation, how does the pseudocode change on each of these? For example,
No, the pseudocode's identical. That's my point. The literal same function sigma will reduce HP to null bar, all empty, and fin bar. The same construction because it's sigma star and empty. Oh God, we have 3 minutes. Okay, we can do this.